at. So this would be the main idea or main construction from this Kohler-Shepard-Barn paper from '89. And so, suitably extended. And so the idea is this. So we're, say we're starting with the moduli mg of curves of genus G, and G is at least 2. And we're trying to guess this compactification mg bar. And so we're trying to guess what's on the boundary. And so to find those curves, stable dealing curves on the boundary, of course, we're looking at one-parameter degenerations. And we would like to see if every one-parameter degeneration somehow has a canonical limit. And so those canonical limits will be the stable curves that we need to add. And so once we understand this construction, then maybe we can do it for surfaces. And again, if we have this moduli space of surfaces of general type, so maybe with canonical class ample, maybe smooth surface, so and this is M. And so we're trying to compactify it, construct some stable surfaces, then maybe we should do the same. So once we understand this one-dimensional case very well, maybe we'll just mimic it. And those constructions of one-parameter degenerations, maybe they will give us the right answer. All right, so if you've never seen this before, I'm sure you have. So let's do it for curves. So you start with the one-parameter family of curves, and it's not complete. There is nothing in the central fiber. And so then the first thing you do, you apply the stable reduction theorem. Stable reduction theorem, and which says that after maybe a finite base change, there is a family like this, which is very nice. So there is a family X to this curve C such that X is smooth and the central fiber is simple normal crossing. So that's the first step. But then, of course, such a family is highly non-unique, because if you have one such family, you can always pick a non-singular point in the central fiber and blow up and do it again. And so there are infinitely many such families. And so you insist somehow on uniqueness. And so what you insist on, you ask for the canonical class in the central fiber, you ask for it to be ample. And which means, again, that so for any reducible component, the degree of this dualizing sheaf restricted to E must be positive. And I'll remind you the formula. That was the formula for this number. And so this fails to be positive precisely in two cases. When you have a free-hanging P1, which only intersects the rest at one point. So this is -2, and this is -1. And such a curve is a -1 curve. And also a P1 like this, which intersects the rest of the curve in 2 points. So then in this formula, you get -2 + 2. And so this is a P1, which in the smooth surface X is a -2 curve. And so what you must do is you must contract the -1 curves and then contract -2 curves. So starting with this family, you have to do 2 steps. You have to replace this family by a new family where you contracted all the -1 curves in the central fiber and the -2 curves. And so most students of algebraic geometry will recognize that when you contract the -1 curves, then you construct the minimal model. And it's because you only do it in the central fiber, it's a relative minimal model for this morphism. And when you also contract the -2 curves, then that's called the canonical model. So you contract, for this initial first guess, you can construct the canonical model. So that's the idea. So the idea of Kohler and Shepard-Barron was to do the same for surfaces. And so starting with the one-parameter family of surfaces, you can apply the stable reduction theorem and arrive at the first guess when the central fiber is, when the family is smooth and the central fiber is normal crossing reduced. And then that will be just the first guess. And so after that, you should replace it by the minimal model and then by the canonical model. And so by that time, the minimal models were known for threefolds, so they could do it for surfaces. And now the minimal and canonical models are known in all dimensions, so we can do it in all dimensions. Now, a version of this construction is if you start with not just a curve, but a curve with points. And those points, PIs, or maybe I will call it BIs, you can consider them with coefficients. And so then these canonical and minimal models will be, so these will be models for a pair X, sum of VI, VI, where these script VIs are now the divisors on the family. And so that's what you should do in higher dimensions as well. So if you start with a pair, not just one variety, but a pair, then you should apply the stable reduction theorem for the pair and then find the canonical model for the pair. And so canonical, as the word canonical implies, it has a certain uniqueness property. And this gives you the uniqueness of this nice limit. So that's, now when you do this step for in the case of degeneration of curves, this step is very explicit. So you just contract all the free-hanging -1 curves in the central fiber, and then contract, it turns out to be chains of -2 curves in the central fiber. And in higher dimensions, this is absolutely not explicit. It's just there is a general theorem which tells you that this minimal model exists and this canonical model exists. And for threefold, there is still some explicit geometry that you can do. And for higher dimensions, it's just a theorem. But what you know from this, you know that the canonical model, as I said, is unique. And so that allows you to conclude that the limit is unique. And it allows you to formulate what the stable pairs should be. And so let me put it again here. So the stable pair is a pair like this, where X is projective, reduced, reduced connected, and BIs are Veil divisors. And the singularities of this pair are semi-log canonical, and kx plus b is ample. So now maybe I can attempt to answer what the semi-log canonical means. And the simple answer is it's whatever you get out of this construction. And now the canonical model, it's canonical model for a pair like this. So the minimal model program says that this model has log canonical singularities. And then you have to look at the central fiber, and the central fiber will be non-normal, will have several irreducible components. So you have to compute or have to figure out what that central fiber, what kind of singularities it has, and so you just call them semi-log canonical singularities. So they are let me give a definition, even if very quickly. So if we have a pair, then we say that it has semi-log canonical singularities if so one has to be nodal in codimension 1. X has to satisfy Serre's condition S2, so which is a substitute for normality for such nodal varieties. And if nu is normalization, then the pair x nu preimage of the divisor plus the double locus. So this pair has to be log canonical. And again, log canonical is, that's the kind of singularities that canonical models have in the minimal model program. Well, and so then that's a simple answer why it's Veil divisors and not Cartier. It's because it's we cannot just wish for things. The singularities should be whatever we get out of this construction. And so when we do the minimal model program, when we construct the canonical model, even if we started with something very smooth, the divisors BI here will be only Veil divisors and not Cartier divisors.
So what does Veil divisor mean? Cartier divisor in codimension 1.
Right. So Veil divisors, and so let me add this number 4 here. And so B should not contain any irreducible component of the double locus. And number 5. So some multiple of kx plus b has to be Cartier. And I could let me just leave it at this. All right, so what I will attempt to do, I will attempt to give a general outline for these cases, and let me put the case of toric varieties again, and then of abelian varieties. And my directed graph, it went like this. So let me show some of this story the best I can in the time I have. And so let me begin from the beginning, and that would be this case 1. And let me begin with toric varieties over X over P. So let's say X is a toric. XL is a projective toric variety, and L is an ample line bundle. Then an object like this, almost the same thing as a lattice polytope. So if on X we have an action by a torus T, and let me work over complex numbers. So let's say it's C star to the n, then to give a pair like this is the same as to give, to specify a lattice Z to the n, and then in it to give a polytope. And lattice polytope means that the points of it are integer vectors. So that's a lattice polytope. And so this lattice polytope, the polytope is defined up to a translation. Now, I said over Pn, so what do I mean by this? Now, if you look at H0 XL, then that's a direct sum over these integral points. Q intersect Zn of one-dimensional spaces, the character spaces. Now, this collection x lambda, so defines a map, a morphism. Well, let's start with a map. x from x to Pn, where n is, well, it's the number of these integral points minus 1. And the most basic fact that we know about this is that this morphism f is a finite morphism. Is a finite morphism. So it doesn't have to be an injection. Doesn't have to be a one-to-one, but it's always a finite morphism, and it's some combinatorial condition on the polytope for it to be an embedding. Now, the most basic moduli spaces underlying all of this is this. So we can look at, instead of this collection, we can twist it by some coefficients and consider this twisted map. And so far, nothing much happened. But then we can consider the degenerations of such maps. So the most basic moduli space is the, I will call it M, T of Q, P, N. And so this is the moduli space of stable toric maps. To Pn. So what I want to do is I want to start with such simple maps and then consider their moduli space. There will be some positive dimensional moduli space. And then I'd like to see what happens when a map like this degenerates. And so the answer is quite simple. So what happens, to understand those stable maps, again, I have to consider a one-parameter family and see if I can construct a nice limit in this one-parameter family. And so a one-parameter family will look like this. So we'll be given by some collection C lambda of T. And T will go to 0. And so as T equals goes to 0, those functions of T, each of them will have a leading term, so which I can isolate. So there will be some power of T that can be factored out, and the rest will be non-vanishing. And so what that tells me is that for each of these integral points lambda, what I have, I have a height, so which I denoted by this h lambda. So I have a height function. So every one-parameter family gives me, so a one-parameter family gives a height function h, and it's from the integral points here to z. And so this height function tells you what the limit of this toric map is. And let me draw a simpler version. This is a two-dimensional picture, and it's a little hard. Let me draw a one-dimensional version. So this is q, and it sits in z to the 1. So if I have a height function in this case, then let me tell you combinatorially what happens. So what happens is that this toric variety for the polytope Q splits into several toric varieties, and as given by the convex envelope, by the envelope of this height function. So in this particular case, when I started with toric varieties corresponding to this polytope, and they would be just P1 with the O3, with the sheaf O3, and given this height function, it's split into P1 with the sheaf O of 2 and another P1 with the sheaf O of 2, O of 1 and O of 2. And so this, here it's a little harder to draw, but this polytope will split into several polytopes, and so this toric variety will split into several toric varieties, which are glued according to this picture. And in the limit, so the limit of this family will be a map from a variety that looks like this. So stable toric maps are, let me say what they are. So these are maps X to Pn, which are finite morphisms, and each X is a union of toric varieties. And a semi-normal union of toric varieties. And so this is the most basic case and the most elementary. To describe this moduli space, to understand what all of these stable toric varieties are, all you have to understand is what the subdivisions of the given polytope Q are into smaller polytopes. So this empty bar is a disjoint union of strata, and each stratum corresponds to a lattice subdivision of Q. So if you start with a polytope, then you consider all the way you can subdivide it into smaller lattice subpolytopes, and for each of these subdivisions, there will be varieties that look like this, and maps to Pn. Now, a version of this construction is that if you look at a moduli space not over Pn, but over some closed T-invariant subvariety or subscheme of Pn. And so then in this case, you insist that the image of this stable toric map is not arbitrary, but is contained in this subscheme Z. And so what the consequence of this is that then the strata correspond not to all lattice subdivisions of Q, but only to some of them. So the restriction that the image is in Z tells you that there will be only some of these subdivisions, and there are lattice subdivisions. Now, so that's this case number one. So number two is an application of this construction, but which goes through the Mumford-Tates construction of degenerating abelian varieties, which tells you that if you have a one-parameter degenerating family of abelian varieties, then near the boundary, you can model it on a toric picture like this. And the difference, with the only difference that instead of this polytope and a height function h, what you should do, you should consider z of g, and instead of those c lambda of t, you will have theta lambda of t. And so these are the coefficients for the theta function, for the degenerating theta function. And so when you expand them similarly, and identify the principal part, the power of t, just as in that example, then this function h of lambda, it will be quadratic, positive, definite function on z to the g. And so in this picture, when taken the convex hull, you should take the convex hull of, instead of an arbitrary height function, it should be a height function of a quadratic positive definite form. And so the consequence of this is that for the compactified moduli spaces, a space of abelian pairs. It's x epsilon d. The strata now correspond to periodic. So subdivisions of Rg into polytopes. So let me give an application, a quick application of this to computing this example. So let me just tell you what the degenerations of all of these theta divisors are in the principally polarized abelian threefolds. So how many of them there are, and etc. So what we begin with is, so this will be the case 16. This will be the theta divisors in the principally polarized abelian varieties of dimension 3. And so the preliminary statement here is as follows. So we start with the space A3, and this is the moduli space of principally polarized abelian varieties of dimension 3, and the dimension of it will be 3 times 4 over 2, so it's a 6-dimensional space. And every point of this space is an abelian variety, together with the polarization. And to begin with, one identifies it with the moduli space of abelian pairs, whose points are abelian torsors. So this is the abelian variety without the origin fixed, and theta is well, it's a theta divisor. And so that's the moduli space which we need to parameterize. And so what this theory says is that to classify them all, to compactify this space, and to see what the varieties are on the boundary, we have to construct all such ZG periodic subdivisions of Rg. And then, so this is somehow, this is almost what we want, but this is the moduli space of pairs like this. And if you have a pair like this, we can deduce from it, well, we can just look at the divisor D itself without the, we can forget the ambient abelian variety and just look at the theta divisor D. And a priori, this could be a different space. But the theorem here is that we can go back and forth. So if you start with the divisor on the principally polarized abelian variety, then you can recover from it the abelian variety as the Albanese of D, and the embedding of D in it as the Albanese map. So you can go back and forth, and it doesn't matter whether you look at this theta divisor on its own or on a pair like this. All right, so I'll start easy and tell you what the Z2 periodic subdivisions of R2 are. And so these we can list very easily, and this subdivision will be where I don't subdivide at all. And this is the subdivision where I subdivide a little, and then there is a subdivision where there are two of these subdivisions where I subdivide a lot. And so these correspond to just abelian surfaces, and this is the first order degeneration, and in this case, this variety is a P1 cross P1 glued to itself. And in this case, I have P2 and P2 glued. And the divisor D is given as a divisor in the storic variety, and it's so D is given by some function f, and if I restrict it to one of these storic varieties xj, then this function fj has the Newton polytope the corresponding polytope Qj, which means that in this case, this theta divisor will be, well, the storic variety is a P2, and the theta divisor is given by a function whose Newton polytope is this triangle itself. So it's a line. In this case, it's a line, and in this case, this is a P1 cross P1, and the theta divisor is a quadric. So the story for the three-dimensional three-fourths is exactly the same, only instead of these two-dimensional pictures, you have to list all the three-dimensional pictures. And the answer is, well, it's almost the same. So these Z3 periodic subdivisions of R3, they are given by cutting by hyperplanes. Just in this case, all of these subdivisions were by cutting one hyperplane or two hyperplanes or three hyperplanes. In dimension 3, this is still one cuts R3 into cubes, and then there are also, so the maximal subdivision will correspond to 6 P3s. So cutting this, dicing this cube into 6 small simplices, and this space will be smooth, will be a smooth stack. It will not be. So in dimension 4 is the last time where these. So now it's a question of combinatorics. So what are the periodic subdivisions of Rg, which are periodic with respect to Zg? And actually 3 is the last number where the answer is nice. And so in higher dimensions, in dimension 4, the answer is completely known, and it's not even known for dimension 6 and higher. So the upshot of this is that you get a smooth moduli space of dimension 6 this way. And you can describe every variety that appears on the boundary by analyzing these pictures. And so the maximally degenerate ones will be just glued from toric varieties and a maximum of 6 of P3s. And the divisor will be just given by a polynomial on each of these toric varieties.
Is there any relation to the corridor complication of AC?
To what?
Corridor complication of AC.
So that I should say. So this is a toroidal compactification for one special toroidal compactification. This is the second toroidal compactification. Let me quickly move to this case and indicate how this works.
So the generic data divisors as being nice, in terms of singularities?
So they are semi-log canonical surfaces. And so each of them, that was the explicit description of them. To describe any of them, one should just take this degenerate abelian variety, for example, the union of 6 of P3s. And on each of the toric varieties, you have a polynomial that has this Newton polytope, this polytope. And that gives you the theta divisor. And so in this maximally degenerate case, it will be just a union of 6 P2s, the theta divisor. And they intersect the way these 6 simplices are glued to each other.
So my question was, is it automatic that the singularities are nice of the degenerate data divisors?
So this is not an automatic. This is a theorem, though, that the singularities of the theta. So the theorem is this. Let me put it on the board. So the theorem is that this pair. So in the principally polarized case, this pair has semi-log canonical singularities. which by adjunction means that the divisor is semi-log canonical. And it's not automatic because by the construction of the moduli space, only this pair was semi-log canonical. And so this is somewhat non-trivial theorem. Well, let me move on to this case. So in this case, there is nothing toric, so it is somewhat surprising that this toric theory still applies because, well, there is no group action. And so the way it works is through the following construction, which goes back to Kapranov. And the construction is, well, if we just look at the ordinary Grassmannian of R-dimensional spaces in Cn, then that can be embedded by a Plucker embedding into this space. And if we fix this ambient space in very V, then on C to the n you have an action of torus, C star to the n, which implies that, well, on this Grassmannian you have an action of a torus of one lower dimension. And so then I can apply my previous construction and I can look at these toric stable maps into this Grassmannian. And this polytope will be the convex hull of points like this. And each of these points corresponds to a Plucker coordinate. Like that. Now it turns out, you know, almost by magic that this moduli space describes not only, you know, a point of this moduli space is just a map. Let me call it Y. Is a map to the Grassmannian. And it turns out that this map is an embedding. And it's some kind of toric variety, either a toric variety or a limit of it, a stable toric variety, which similarly has nothing to do with this configuration. So what happens, though, is that inside of this Grassmannian, there is a smaller Grassmannian E. And so this is all the spaces that contain the point 1, 1, 1. And if you intersect this Y with that smaller Grassmannian, then that can be identified with the with a stable pair like this, or is degeneration. And so this compactification is obtained indirectly through a construction like this. And now because this is a moduli space of the form that I started with, the strata of this moduli space. So there are in one-to-one correspondence with the, so I call them Z subdivisions of the lattice polytope Q. And so just to describe this moduli space completely, one has to answer, first of all, what is this polytope, and then secondly, what are the Z subdivisions. So if this stable toric variety mapped to a projective space, then we would look at all the subdivisions of Q. And because it only maps to a Grassmannian sitting inside, then it's only some special subdivisions. And so the polytope Q, well, that's the answer for it. And this polytope can be written differently in this form. So it's and it's called the hypersimplex. So this is the hypersimplex delta Rn, and this Z subdivisions. So Z is the Grassmannian. The answer to that this should be a subdivision into, not arbitrary, but into metroid polytopes. Now I'll have to stop pretty soon, but once you understand this story, then maybe I'll tell you quickly how it flows through those other cases. So this story was, this construction was due to Hakenkill, Tevolev, and Kapranov. And that dealt with the case when this coefficient, all these coefficients were 1. And so the way it generalizes to this case is on the outside, it's a very simple modification. And so instead of this hypersimplex, one considers a weighted hypersimplex which is just given by these inequalities. Now in the case of Bournier surfaces, in the plane in special position, and by blowing up these 3 points, they can also be transformed into a configuration which is more symmetric. and then collapsed the other way into another configuration on. So this is in the plane, and this is the blow up of the plane at 3 points, and it can be collapsed into another P2. So in this case, the polytope that one considers is what's natural to call a Bournier polytope, and it is a polytope in subpolytope in this hypersimplex with the coefficients 1/2 and so it lies in this hypersimplex in 2 different ways, and this is sort of the minimal polytope that can be embedded into both of them. Yeah, unfortunately, I think I ran out of time, so I'd better stop here.
Can you say basically how the line configuration gives you the very output?
Right. So here's what the general theory says. So the general theory says, if you want to understand the degenerations of this polytope, of this configuration, and so once you have this configuration, then you construct the surface of general type by looking at ramified cover, which is ramified. It's a 4-to-1 cover, which is ramified along the configuration of these lines. So what are the degenerations of this? And so the theory says then you should look at this polytope, and it lies in this polytope delta 3,9. And so here you know what all the Matroid polytopes are. And so you should consider all the ways you can cover this polytope by Matroid polytopes. And each of these ways will give you a degenerate surface. And so the simplest degeneration that you can look at is, let me just draw one degeneration for you. And so this degeneration is, let me try on the fly. And so in this degeneration, this is a blow up of P2 at 3 points, and it splits into three surfaces like this, which are P1 cross P1, each of them, and those lines they split like this. And so what this degeneration means is, well, it's a union of three surfaces. Each of them is P1 cross P1. And you have this configuration of ramification divisors. Now, the way it comes from a computation is that you start with that polytope, and you write it as a union of three smaller polytopes. And now this cover, this degenerate Bournier surface in this case, it's a cover of this, and it's ramified. It's abelian with the group Z2 squared. And so pre-image of this surface is a 4-to-1 cover, which is ramified into, well, those Oh. I see what, I think I messed up the colors a little bit. But this is a union of 3 bielliptic surfaces, and it's a normal crossing union. And so then to classify them all, you should, or I should, consider all the way this polytope can be subdivided. And there are 10 cases. And so for each of these 10 cases, there is a picture like this. And then this tells you what the surface is. And
That divisors?
huh?
You say that there are 10 cases that give divisors?
Right. I think 8 of them give divisors, and 2 give deeper strata. And so those other Bournier cases are instead of P2 or blow up of P2 at 3 points, one considers a configuration which is more special, even more special than this. And so, for example, a configuration in which this red line and this blue line and this yellow line, they pass through 1 point. And then this surface is that we begin with is not the blow up of P2 at 3 points, but blow up of P2 at 4 points. And so one has to describe this moduli space, one has to analyze the degenerations of this configuration. And so for that, there is a smaller polytope for so to analyze all the strata, one has to describe all the subdivisions of this into smaller polytopes. And one gets a smaller dimensional space.
Okay, so second speaker again.